Thank you everyone for joining us today. We welcome you from wherever you may be to this webinar on direct georeferencing for agricultural research. We're going to take you through a number of segments here in the presentation today. We'll talk a little bit about what direct georeferencing is, and then we'll get into a case study. But the first thing I'd like to do is just introduce our team today that we have online. My name is Brad Schmidt. I'm the Global UAV Sales Manager here at Applanix. Today with us is Matt Bechtel from Griffin, who is the CEO there, and we also have with us Evan Flatt, the Director of Solutions at Griffin. Also, just a few things logistically and support-wise. We do have Kurt Bioletti on the line, who is going to basically handle the questions for us today. So if you do have any questions, please enter them in that questions box, maybe during the presentation, and we'll get to those questions at the end. And also we have Cynthia from our marketing department online, who's kind of managing our platform in the back here to make sure everything kind of runs smooth. So that's our team for today, and we really hope you enjoy this presentation. The format for the presentation will be about 40 to 50 minutes long, and then we'll take about 10 minutes questions at the end. We'll certainly try to keep this within an hour. I'm sure we can do that. And also the presentation will be recorded, or the webinar will be recorded, and we will circulate that. So everybody's on mute right now. And as I say, if you want to communicate with us for questions, etc., just enter that in the enter that information in the questions box, and we'll be happy to get to those at the end of the presentation. So our agenda is we're going to basically talk a little bit about the companies. I'll let Matt from Griffin introduce Griffin later on in the presentation once we get into his material and Evan's material. We're going to look a little bit about or at what direct georeferencing is. I mean, many of you who are attending may be quite familiar with direct georeferencing, but there may be those who are not. So we'll just review that very quickly. And we'll take a look at how UAVs are deployed in the agricultural mapping segment. And we'll get into some of the benefits of direct georeferencing for agricultural mapping. After that, we'll get into quite a bit of material from Griffin regarding direct georeferencing and agriculture. And then, as I say at the end, we'll wrap up with a Q&A, and we'll take your questions at that time. If we don't get to all of your questions in the webinar, we will circulate answers subsequent to this webinar presentation. So just a little bit about Applanix. We were formed in 1991, a spin-off from Honeywell. Our focus is mainly on inertial systems. And we've developed those over the years for the land, marine, and the airborne industry. We were acquired by Trimble in 2003. Trimble, of course, as you may know, is a leading supplier of GNSS technology globally. So integrating that GNSS technology with the inertial technology from Applanix, we're able to create some fairly unique solutions for direct georeferencing and positioning data. So that's basically who Applanix is. We've been around, as I say, since 1991. And our pedigree is really in inertial systems, integrating it with GNSS, and we've developed that over many years, certainly in the manned airborne segment or the crewed airborne segment, and then now in the uncrewed segment as well. I'd like to start my presentations off with a bit of a quote, and this is one from Fortune Business Insights. I like this quote because it really kind of states where UAVs are with respect to agriculture at this point in time. It says, and I'll just read this for you, it says, the emergence of smart agriculture technologies in precision agriculture is projected to fuel demand for agricultural drones in the coming years. Unmanned aerial vehicles are playing an important role in carrying farming operations in advanced farming management and site-specific crop management, owing to the excellent capability of these drones in aiding with maximization of crop production. A bit of a mouthful, but certainly loaded with a lot of important information related to UAVs in the use of in the agricultural market. So certainly one of the key markets. In fact, this is the first of our a series of presentations we're going to be doing on applications with respect to using direct georeferencing and UAVs. So, but this is a very important area, the agricultural area. So some of the ways that UAVs help with agriculture, certainly things like plant phenotyping. I believe Matt and Evan are going to talk a little bit about that later on in their presentation, but for many and many other areas as well too, soil mapping and field analysis, collecting that data, crop management. One of the things we're starting to see here more at Applanix is basically the use of not only autonomous vehicles on the ground for basically doing farming operations or agricultural operations, whether it be crop spraying or fertilization, but we're also seeing the link of that to UAVs for the collection of that data so that the applications can be very specific and very focused in terms of agricultural management. So, an integration of autonomy now and UAVs, and there's some very, very interesting applications out there, but I won't necessarily get into all of those details today. Certainly for monitoring crop health and monitoring that crop health. I remember when I first started out in the remote sensing industry, we were doing this using satellite imagery. And the resolution wasn't very good. I'm kind of dating myself here, but now with UAVs, we can get very, very accurate information on crop health right down to the plant level. So just amazing stuff that's going on with respect to using this technology. So one of the things I wanted to do was just refresh your memory on what direct georeferencing is. I mean, there may be some of you out there who are not familiar with direct georeferencing. So let me just kind of use my own words to describe what it is. And there's some information here on the screen that you can read as well in terms of the value of direct georeferencing. But essentially what we're doing is we're using that GNSS system for collecting positional information, and then integrated with an IMU or an inertial system, we can collect the orientation data. So with the imagery, the orientation information, the positioning information, we can tag those each of those images that is collected, or LiDAR data points in the case of LiDAR. And we can use that information along with other technical specifications like setting lever arms, and if you're using a camera calibration data. That's all mathematical. We can basically take that mathematics and then position those points on the ground exactly where they need to be without the need for ground control points. So the big value here is basically in time and cost savings. So that is one of the key values of direct georeferencing to the UAV market, whether it be agriculture or any other market. So I want to take just a moment and just discuss why DG is important to agriculture. And there's really three areas or three reasons, or at least three that I've chosen to present. And I think there's more for sure, but I think the top three reasons are basically the achievement of precision and accuracy. And of course, precision and accuracy are two different things. Precision is related to really the grouping. Say, for example, if you're shooting LiDAR data points, the grouping of those points. Accuracy is how well those points are positioned relative to where they're supposed to be on the ground. So you can see here on the left side that we don't have any kind of precision or accuracy with our points here. Basically, if we add GNSS or if we add an IMU, we get very, very good positioning information, but the accuracy is not so good. What we're trying to do is get those points or that data kind of positioned that's been that has good precision, and get that basically where it needs to be on the ground. Or in a case of the diagram that we're using here, to get all the points to line up with the target. So that's precision and accuracy, and that's why it's important to agriculture. This is perhaps one of my favorite slides here. It really helps to kind of show the value of direct georeferencing to using with UAV surveying and mapping, whether it be for agriculture or any other kind of application. And this also, this slide also kind of shows a development over time of the technology. So initially, we've been using in the UAV segment as well as the crewed aerial segment, aerial triangulation. It's been around for a long time. It's a proven technology and it works well, but it requires as you can see on the left-hand side here, that you need quite a number of ground control points in order to tie the imagery, your points, relative points in the imagery, to those coordinates that we collect here on the ground. So if you don't have any control set up for the area that you're flying, you basically need to establish this control and then capture your data that way. But this is a more time-consuming process because there's much more manual steps involved and more steps in general involved in completing your survey using aerial triangulation. So over time, we got a little bit smarter and said, hey, well, what if we just add a GNSS? And what does that do to us? Well, it basically eliminates the need for all of these ground control points that you see with aerial triangulation, and we can eliminate some of those and basically use the positioning information from the GNSS unit to help us with capturing that positioning data and tagging it to the imagery and helping to basically do the georeferencing from that point. And then we said, well, hey, why not just add an IMU or inertial system as well? So what does that get us? Well, that gets us basically, as I explained before, because we can use mathematics to position the information on the ground, we don't need any ground control points. We'll need one or two checkpoints to make sure that the data being captured is accurate, but we don't need all of these ground control points that you need in the other methods that I've got shown here. The other wonderful thing that it does is we don't need that high degree of overlap that you see in the AT method and the GNSS method. And that allows us to basically, for these UAVs that have a shorter flight time span, maybe 20 to 30 minutes, that allows us to fly twice the area in that period of time. So that's another value of direct georeferencing to agriculture. And finally, because if it's all mathematical, we can basically process the data very quickly if that is required. So we have software for that, something called Pause Pack we use for that. I'll talk a little bit more about that later on, but basically what it does is it provides all of those tools to process the data. You can visualize up front the data you've captured to make sure that it's all kind of correct, but then when you process it, it's basically an automated process. So that's another value. So what's required for UAV agricultural mapping? Well, really there's a number of different things. Of course, you need your core UAV and your sensor payload. That's core, and then basically turning that into a professional survey grade mapping solution, you need to add, as I've kind of explained here previously, an integrated GNS inertial system, such as the one I have displayed here, which is our APX-15. You need a correction solution. That could be a physical base station. It could be using a core system, or it could be even using the Trimble PPRTX solution. I'll talk about that in a minute too. And finally, as I mentioned before, our data processing solution. So you bring that all together, and basically that's what's needed for basically doing survey grade mapping and for the agricultural segment. So let me just dive into the technology just a little bit more before we get into our case study. So in terms of being able to capture the orientation and positioning data simultaneously, we have a number of different board sets that we offer at Applanix. So we have the APX-15, which is an integrated GNSS IMU unit. This is our workhorse. This is used for pretty much, I would say, 70–80% of the client requirements that we have use the APX-15. There's a version of it for a gimbal UAV platform. So we basically, with a gimbal system, we put a second IMU on the gimbal, put the main board right on the UAV platform. And then we have basically two sets of orientations, one for the platform, one for the gimbal. All of this data is resolved within the processing software to give us those accurate results. The APX-18 is specific to the kind of inspection, facade scanning, anything where anything where your UAV is moving slow or maybe even being held static and capturing data. This particular unit features a dual antenna configuration that allows us to constrain the heading and again maintain that accurate information in order to capture that. That's kind of important, say for example, if you're capturing a building maybe using LiDAR, and you don't want any kind of drift on your points out toward the edges of those buildings. This kind of constrains all that and makes sure that all of those points, all of those LiDAR points are captured in their correct 3D space so that you have an accurate model. And then finally, our kind of high end or top end unit is the APX20. It has an onboard IMU plus a second IMU. I don't have the second IMU displayed here, but there's another IMU, very, very high end. And this really is required for when you're flying at a UAV ceiling level, so maybe 400 feet, and you want to fly a little faster. So that might be, say, for example, if you're mapping corridors, railway tracks, transmission lines, pipelines, etc. This would be a very good solution for that. So let's just take a look at these augmentation solutions again. This is kind of the second of the three components I talked about in addition to your UAV platform. So for correcting the data, you can use a physical base station. I've got displayed here our smart target, which is basically a target that you can pick up in the imagery, along with a GNSS device, which is in the center of the target here. So this is really for collecting your checkpoint information. And so you can simply toss this into your collection field and start logging that data. It's a very, very simple system to use. It works off of a cell phone. There's an app that you download for your cell phone, and you can basically start the data logging and then take the little chip out of the data logger and then plug that into your computer to take that information and process it through POSPAC. Okay, and we also do offer a cores solution as well, something called SmartBase, Applanix SmartBase, which uses cores networks. The issue here is that it takes about 24 hours to get the results, but if you don't need them right away, then this solution works just brilliantly. It's excellent. And then finally, the Trimble PPRTX solution. This is Trimble's own global correction and positioning solution. So this is a cloud-based solution. We connect to all the different GNSS satellites up there, and we provide these correction facilities either through a satellite band or through the internet to get these corrections. And basically these corrections happen very quickly. Certainly in the areas where we have kind of the dense positioning of these receiving centers, we can capture that information or the convergence of the data very, very quickly within about 5 minutes. So very, very effective for using with UAVs. Now, this is also a global system. You can use it anywhere in the world, except the convergence time takes about, in some places, 25 to 30 minutes. But certainly in Europe and in North America, we have these fast regions where the convergence time is very, very quickly. So you can access that correction data for your UAV mission pretty much right away. Okay, and then finally POSPAC. So this is our processing solution. We have a specific version of POSPAC for UAVs. We have one that has support for all of our different positioning solutions for marine, for crewed airborne, for uncrewed, for land autonomy, etc. That's all supported in POSPAC MMS, but if you're just flying UAVs, POSPAC UAV is a wonderful solution focused on just processing the UAV data. It basically takes your raw GNS data, your inertial data, your DMI data, your base station data, you feed that all into POSPAC, and the solutions coming out the other end are either an SBET file, smooth best estimate trajectory solution, or an exterior orientation file in the case of RGB cameras, say, for example. And we can even produce a point cloud with this software as well. And it's all modular, so we continue to add modules on top of POSPAC to basically enhance the solution as more and more needs are identified. So I think on that note, I'm going to turn it over to Matt and Evan to take it from here. And Griffin is going to really take this and present how you can use direct georeferencing in agriculture and basically the importance of agriculture, to the industry in general. So I think you'll really find this quite informative. And Matt, are you starting?
Yep, we're good to go. Thanks, Brad.
Awesome.
So when you all registered, you saw our introductions and our bios on the main page. So I won't put those here, but for the recording, they're there. You also see our email. So if you need to follow up with us, that's there as well. But again, thank you for your time and attendance today. I know a lot of you are global. We'll be viewing this recording later, so we look forward to following up with you. We're going to take about 20-ish minutes. I'm going to start with a little bit of the background of why we're doing what we're doing and how it's different perhaps than other agricultural applications you've heard of in the past. And then Evan is going to talk a little bit more about how we implement this. Again, this is not intended to be a technical deep dive. It's going to be a fast overview. So we're happy to follow up on any of these components. And then I'll wrap up at the end with a little bit more of a tangible example, some images that our customers see or demand of us from our platform, and how they might use those and how we go about getting those for them. So again, starting off with what Griffin is, our focus is on developing premium sensing solutions for digital phenomics and agricultural research. We have applications far beyond agriculture, but that's really our origin. That's where we started. We were fortunate to be a part of a Terra grant from the Department of Energy ARPA-E program in cooperation with Purdue University. At the bottom of this slide, you'll see a number of the contributors. They were either collaborators in the ag sector or sensor providers like Headwall or the University of Queensland, who is also an academic partner on this effort. But we've been working on this project for several years, and our objective was to commercialize this work. And so a huge thanks to the early origins of that work, and we're happy to follow up with you more on that. So starting with a little bit of context, precision agriculture is really what you probably know most. Thinking about things like satellites and airplanes, those continue to be very, very important to the precision agriculture sector from an agronomic perspective, from a sustainability perspective. That isn't going to change anytime soon. Drones are augmenting that. It's going to be a remote sensing ecosystem of solutions across agriculture, and that doesn't change. So again, over on the right, you'll see some of the objectives of taking imagery and turning it into actionable outcomes like yield and stand and disease and crop health, drainage, etc. These images are very similar to what happens on our family farm. So we've got a 7th-generation farm in Indiana where scale is important. We need to cover a lot of acres. We need to make decisions, and we need to really focus on how do we move from field level management to subfield or zone management, hence precision agriculture. But what we're talking about is really 4, 5, 6 years before that farmer ever really gets the seed. And what we're talking about is phenotyping and digital phenotyping. And so phenotyping is the easiest way to think of it is G by E by M. That's genetics by environment by management. So what are the genetics? What is the environment? Is it hot? Is it cold? Is it wet? Is it dry? And under what management techniques? And breeders use phenomics to try and understand how do we achieve the expected outcomes like yield or drought resistance or disease resistance. And you do that over years and years of time of selection. And that's very, very slow. It's labor intensive. It's often highly subjective, and it's very expensive. And so as many things in this world, we're turning to sensors and sensing to try and get a better understanding of how do we make these decisions better? How do we make them faster? How do we free up the time of these very well-educated, very smart breeders that are out there doing lots of other things when we really want them focusing on other priorities? So we're looking at things like drones and remote sensing to help in many, many ways. And every company, every academic organization has different priorities, different crops, etc. From a commercial sense, this is also a huge numbers game. And so just as a gloss over this, to give you some context from a business perspective, it takes about 4 to 6 years of breeding to get a genetic trait essentially to market. So it takes a very long time. And of that sample, really only about 3.5% of offspring have some sort of elite improvements. And then the real elite is a fraction of those. And so what you're really trying to do is say, how do we use these tools? How do we use breeding and phenomics to eliminate the dogs and not even worry about them sooner and really focus on that elite? And that's whether it's strawberries, whether it's corn, whether it's wheat. How do we get that to the producer's market better and faster? So when we're talking about remote sensing, when we're talking about precision, we're really redefining that And again, thinking about precision ag from the field to subfield level, we're talking about the plant to plot. So we have to give up scale for resolution. We need multimodal, we need lots of things at a very different scale than most in agriculture are familiar with in this space. And it's really why direct georeferencing comes in, and we'll get to that in a minute. So for example, this wish list is a wish list of kind of demands from plant breeders to better understand. And it's things like plant height, standability, kernel size, biomass, disease predictions, etc. This is just corn and popcorn. So every crop has its own unique needs. Every researcher has something that they want to particularly focus on. Some of these are chemical or spectral, since hence multispectral or hyperspectral data. Some of them are physical, like plant height, where LiDAR comes into play, or helping to calculate volumetric biomass, or penetration to understand the impact of sun on weeds under the canopy. And many, many of them are visual patterns from visual imagery for things like machine learning and pattern recognition. And so when you think about these demands and how different those are across time and space for every different researcher, and I'm waiting for the slide to go, these demand multimodality, meaning multiple sensors. They demand high resolution. They demand precise temporal alignment because we need to honor these things over time. And it demands efficiency. And that is what drives the precision, accuracy, and repeatability needs, and hence direct georeferencing. So I'm going to turn it over to Evan, and he's going to talk a little bit about how we implement that in our approach, and then I'll come back with some examples at the end.
Thanks, Matt. So Matt sort of hit on this, but I just want to address sort of the challenge of doing some of this high throughput phenotyping in an agricultural settings when you really need precise and accurate data. So there's a lot of things that go into data collections like this. You often have complex sensors like some of the hyperspectral and multispectral sensors. You have to worry about spectral calibrations, potentially ground control. Weather is often a very large factor, and then just system reliability. And all of this technology is out there and it's available, but oftentimes it's not easy for a user to actually go out in the field and collect this data, come back, process it, and get what they need out of it. And a lot of the commercial solutions you see for the agriculture market are not always adapted to these really the high accuracy and precision needs that a lot of the plant breeders and researchers need. So I want to talk a little bit about some of Griffin's tools, what we've designed really for agricultural plot research from the start, how we're implementing multimodal UAV-based platforms to do this, and how direct georeferencing falls into that, and what we're doing to streamline the data processing. So I just want to show this really quick and talk about some of the workflows for remote sensing using UAVs. I want to start out saying that oftentimes the research objectives themselves play a big part in exactly how you're going to conduct the data collection and processing, obviously. So that's going to drive what sort of sensors you're flying, what sort of platform you're flying them on. And then once you've decided that, there's a lot of things that go into the system calibration, which Brad mentioned briefly. You have calibration, data collection itself, and then analyzing the quality of that data, processing, and then going on to data analytics. So I've sort of outlined here where Griffin really takes its core approach and what problems we're trying to solve in this workflow. So I want to talk a little bit about some of our specific remote sensing solutions for our research customers. Griffin's working with multiple sensing modalities, either line scanning hyperspectral cameras, 3D LiDAR, high resolution RGB cameras, thermal imagery, and of course, GNSS inertial solutions from Applanix. What we're doing is try to simplify some of those sensor operations for the user as much as possible. So essentially making LiDAR, RGB, and GNSS data collection as push button as possible, but still providing what we call sensor sovereignty. So sensors are able to be operated independently, and users can customize a platform with or without sensors and have the ability to swap models and that sort of thing over time as the technology changes. Another one of the key components of these systems is having accurate and stable calibration. So the bore sight calibration, lever arm, and rotation angles that Brad mentioned earlier are really key to having accurate and precise data processing. And then, of course, having an adaptable design, so a user can mount a sensor payload on different UAV platforms with different sensor configurations. So to that point, I want to talk a little bit about our sensor integration. We've designed a custom multi-sensor control, data storage, and user interface for our systems. It includes a small onboard computer and wireless connectivity for the user to interface with. We try to remain platform agnostic in our integration as well, so we don't have any reliance on the UAV system or platform itself for navigation, data processing, that sort of thing. I touched on this on some previous slides, but we also like to keep inter-sensor dependencies eliminated or to a minimum. So we want to be able to customize systems for our users as much as possible, so they can be customized with or without individual sensors, and this allows for flexibility when you want to do things like upgrade when future sensor models come out, and you don't have reliance on any particular sensor, say for control or data storage of another. So that's really key when you're trying to remain flexible for your hardware. And then we want to also keep the operations as streamlined as possible and just meet customer needs there. So that's sort of our philosophy when we're doing our sensor integration. So regarding our sensor integration, I want to talk a little bit about sort of our standard platform for agricultural research, what we call the Sahara system. So in some of the previous slides, you might have seen our system mounted on a DJI M600 UAV. Since those are being phased out, we're switching over to a FreeFly Alta X UAV platform. But on the sensor side, as a sort of standard configuration, we have the Veneer hyperspectral sensors from Headwall. We're using Velodyne VLP series 3D laser scanners, and then high resolution full frame mirrorless Sony cameras for that high resolution RGB imagery that Matt mentioned. And of course, we're using GNSS inertial solutions from Applanix in the APX15. So processing these data sets requires a few different software packages. So first, the Applanix PostPack software to post-process the trajectory and get an accurate trajectory so we can orthorectify all of this data. We have our software, which actually does the data processing from each of the data types. And then we have software from Headwall as well to do radiometric calibrations. And then we also include some supporting equipment in our base configuration. So that would be reflectance calibration targets for reflectance calibration in the field, batteries, of course, to operate the UAV, and then any sort of training, onboard data storage that a user would need. And of course, we can customize these for the user as well. So with having these multimodal systems where you have multiple sensing modalities on a single platform, the key part of this is really the direct georeferencing. So the user can actually have accurate and precise repeatable data over their collection area. So this little image just sort of illustrates what goes on in that process. And essentially what we're doing is trying to take each of the data points from these three sensor types and align them in a common mapping frame over time. And the key component of that is having the GNSS inertial solution. And then all of these lever arm and rotation angles you see here are how we define the relationship between each of the sensors relative to the IMU. And this process of determining these relationships is, again, key to how accurately this data is processed. And so how we do that, we have what we call system calibration, where we fly a special flight configuration over some different types of ground targets in the field and process this data. So this is a sort of a once a year process we do on a system, either to get the initial parameters or to check the stability over time. So I won't go into a lot of detail on each of these, but for frame cameras, we're using GCPs on the ground to do the calibration initially, and then of course after that, when we're doing our normal data collection, we don't use the GCPs in the processing. We have what we call profile-based LiDAR calibration, where we're aligning profiles from these vertical features in the field from different viewing angles. And then we also use the GCPs for our push broom-based calibrations for the hyperspectral sensors. And this is just an image of what that sort of flight trajectory might look like for one of these calibration flights. So the output of those calibrations is pretty important. This lets us do things like remove distortion from frame camera lenses. We have much better alignment between individual passes in a hyperspectral data cube. And then we have much better alignment of features in the 3D LiDAR point clouds. And I just also wanted to throw in here some independent assessment of this calibration from some of our partners and customers. So just looking at the accuracy of a system like this that uses direct georeferencing and precise calibrations versus a sort of standard off-the-shelf DJI Phantom RGB unit, where we're looking at 3 to 4 meter RMSE on known ground coordinates for the Phantom, and our system is on the order of 2 centimeters in the RGB data and 6 centimeters in the hyperspectral, which is less than 2 pixels. So once we've determined the calibration and the multi-sensor integration, I want to talk about our user-facing software, so how we actually process this data, and a little bit about our philosophy there. So our philosophy has really been minimal user interaction with the software, trying to streamline the data process as much as possible, and keeping the data consistently organized. So we do this through what we call a batch processing pipeline. So users are able to queue multiple what we call jobs in a stack, and then process those with consistent configuration over time. And we're using industry standard formats in a very transparent processing process. So it's not trying to be a black box. We give access to the user to adjust as much of the settings as possible. So sort of the basic workflow here is we do what we call a bundling process, which gets back to the consistent data organization. So bundling all of the acceptable data formats into a common structure that you can use over time. Defining a pipeline, which defines how we want to process a data set, and then submitting that bundled data set to the pipeline to be processed. And then, of course, we can watch that happen over time and see how the status is coming along. And this also includes doing reflectance calibration for the hyperspectral imagery. So just to highlight some of the ways we're using the Applanix and Trimble solutions, I mentioned on our hardware side, we really like the APX15 for its the GNSS inertial technology to give us that accurate trajectory that we need to do the direct georeferencing. We also have the Smart Target that Brad mentioned, which uses an SPS 585 receiver. We also have a Trimble Alloy GNSS receiver that we'd like to use when we want really high quality base station data. And on the software side, we're of course using Postpack, Applanix Postpack, to post-process the trajectory data. And we've integrated that to work seamlessly within our software. So our software actually will run Postpack UAV in the background, so that really allows for a seamless integration for the user experience. And within the Postpack system, we're using SmartBase. Like Brad mentioned, it's been really great for processing when you have a good distribution of core base stations. So now that I've given sort of a basic overview of our hardware solutions, I'm going to turn it back over to Matt to talk a little bit more about how you might use these hardware and software aspects for a user.
Thanks, Evan. So we're going to take just about 4 or 5 minutes, just walk through some examples and some outcomes, so you have a little bit more context of what these outcomes look like. And then obviously at the end, we'll take some questions, and please, as we talked about at the beginning, use the chat, use the questions down there, and we'll take care of those. Let's see, here we go. So from a research perspective, putting this in context, and I'll have some summary points as well about direct georeferencing and the value prop for us. So what we're really trying to do is provide value to researchers to one, take the lab to the field. How do you bridge what we would call a controlled environment or a greenhouse and the field, and then how do you over time continue to increase that scale? If you're planting 32,000 to 40,000 seeds per acre in a production environment, and you're looking at the field to subfield level, that's one problem. When you're trying to essentially image every plant, that's a whole different scalability issue in terms of resolution and such. And so those are the things that we're working towards. As Evan pointed out, we're also working hard to make it easier to use. They're still research tools, they're not toys, but we are trying to make them as easy as possible and reliable. And as we talked about with sensor sovereignty and interdependence, if and when something does happen, you're not completely out of luck with other data sets. So we really value the time of researchers in the field, and we try to make that as efficient as possible. And then lastly, getting back to DG, it's about delivering quality, precision, and repeatability. Many of the tools that we've talked about are seen in precision agriculture, were not built for precision agriculture. They were built for consumer markets, and we've adopted them. Here in recent years, more vendors have come up with some good tools, whether they're drones, sensors, applications, and software, specifically for that community, and that's great. But we're talking about the other end of the spectrum in terms of quality demands and research needs. And so that's why we've built the tools we've built. And the way we work with these customers is either one, as Evan pointed out, with a standard turnkey sensing solution with hardware, software, training, etc. Two, like in the case of Copri, when they come to us with parts that they've got and they want to integrate it as a custom solution in the Griffin methodology. And then lastly, drone as a service for research. And that's kind of what I'm going to use as this next example for these examples of data outcomes. We'll see if that slide advances. And drone as a service is essentially that. It's, we have the hardware, we have professional operations, come fly for us so that we can then take that data and throw it over the fence to our data analysts, to our breeders, whatever that might be. So that begins with the research objectives. Evan pointed this out in that workflow. It all starts with the end in mind and what you're trying to accomplish. There is no perfect sensing solution because everybody's demands are different. So that starts there. And then in a traditional crop environment, say corn, beans, wheat, etc., we tend to focus on what those crop maturity targets are. Again, it's multi-temporal. You're looking at the plants early in the season for one reason, in the middle of the season for another, and again at the later season parts for perhaps a different reason. And sometimes they're the same because you're monitoring things like biomass or plant height. And then as the season develops, we adjust for maturity. So even in a small state like Indiana, corn in the north and corn in the south are vastly different in terms of planting dates, development time, etc. You have to monitor the weather, temperatures, the growing degree days to figure out where that is. So in this example, that gives you kind of an example for one customer where we have multiple locations and we're targeting maturity for corn and soybeans. And then weather happens. So when you're talking about hyperspectral data, threading that needle is very tight. You're only flying about plus or minus 2 hours of solar noon. You can't have any clouds in the sky. LiDAR and RGB are much easier to get around some of that, but when you're flying all three, again, it's a very tight needle to thread. And so this is an example from 2 years ago where we had a 14-day stretch where there was only one good day to meet not only the maturity target in terms of growth stage, the weather, and solar noon all cooperated. Other days were less than perfect, so we will fly those days as well, and we'll do our best to segment that information. But this gets you again into some of the additional challenges that come with research-oriented sensing as opposed to production-oriented sensing. And then we'll use as many tools as we can to monitor things like the weather. We'll build internal dashboards. This is a simple example from early last season where we're thinking about wind conditions. When you're sending a pilot in a very expensive research platform 3 hours away, you don't want to waste time, so you have to make risk-based decisions. Making it easy for the pilots and the managers to understand where the fields are, what to expect, what the flight plans are, what solar noon looks like early in the season, middle season, and late season. So we do as much as we can to be operationally professional to deliver these data sets. And these data sets, again, RGB, LiDAR, and hyperspectral look like we're going to show you here. So again, first in RGB, typically we're using these as 6mm flights. We typically fly at about 44 meters. Again, you can fly lower, you can fly higher. We'll take not only the orthomosaics, but also the sparse point clouds as needed. Most of the applications in this area are around things like plot extraction, looking at the plant or leaf level, things like counting tassels, counting plants, those kinds of things. And increasingly, because of the resolution, machine learning and artificial intelligence applications for pattern recognition, etc. So that's the RGB side. And again, it's all about that multi-data alignment. So I can monitor one little row. So in a field in agriculture, we might go to the subfield. In a research area, we have a field, but we have experiments within that field. Within those experiments, we have plots that might be 10 by 20 feet. And then in this case, we're down to the individual row, and these are only little 10-foot rows or 20-feet rows, depending on the experimental design. We need to come back essentially to that same plant throughout the year to look at that development across time, and DG is the way to do that efficiently. For hyperspectral, in this case, the very near infrared or SWIR, the short wave infrared, depending on what system you're using or both. We have platforms that fly both for ourselves as well as other customers. We'll turn around products like RGB preview so that you can get a sense of what that data looks like. And then we'll turn around the hyperspectral data cubes. And we say cube because you've got an X and a Y dimension, and then you've got a slice for every band that you're turning around. And again, for all of these products, these are all standard industry formats. Nothing's proprietary. So if you're using Open, if you're using Esri, if you're using Envy, if you're using AirDOS, these tools and these data sets will work for our users. And again, for hyperspectral, again, plot or row segment level analysis, you're looking at the imagery, you're looking at what we would call narrow band vegetation indices. Those might be for water absorption, they might be for vegetative health, etc. Obviously, we're getting into phenotypic prediction and using it for things like biomass and flowering and disease and those kinds of things. And we continue to push the envelope in these sectors because a lot of these sensors were only available in very big, very heavy, very expensive airplanes or satellites. And now, because of partners like Headwall bringing them to the drone size, we can get that kind of scale data for these kinds of analyses. And so just going through some examples of those there on the right. And then we're going to switch over to LiDAR. And LiDAR is a fascinating application for agriculture because of plant height, for penetration, and these kinds of things. The video might be a little choppy, but you'll get some examples of the kind of detail row by row that we get. You know, in this case, we're delivering 3D point clouds. Some of them are RGB colorized based on the RGB. You again, at bottom right, you see we're switching to the RGB because you've got that very precise alignment. And that allows us to, again, extend our row extractions, do plot level or segment level extractions, plant heights and volumes, canopy statistics, and penetration indices. And over time, we're going to be able to do more and more with plant structure, depending on operational characteristics, flight parameters, as well as the sensors. And again, all these values are extracted and then available for geospatial analysis. You can take your data in from your field book and you can do your analysis to help assist with your breeding or your research. In this example, we've just pulled out one row from 2 different plots side by side to give you a sense of difference. Again, this is from 44 meters above the earth, and we're taking that data and rotating it like you're actually walking through the field. So there's lots of exciting applications for this as the area matures. This last example for you, these are soybeans. And so this is looking down one segment. So essentially it's about a 10-foot or 20-foot row. And you're not just looking at one plant, but you're looking at that entire row. On the left, you've got 3 different acquisition dates, and all of those point clouds are merged together. You can see what that shape looks like of that plant. And with soybeans, late in the season, the leaves drop, and then you're left with this very interesting structure. But that's what you see here in the September image. So you can see how this data alignment becomes really critical in understanding what this surface area might look like, what the volume might look like, what the structure might look like. But it's all because of that precise and repeatable alignment. So my last slide here, just a couple of takeaway points so that we can go to questions. Some of the value proposition for plant breeding, for research, for phenomics, but also in agriculture research in general. So what does georeferencing provide us? Well, first, obviously, it provides quality. That's precision, that's accuracy, and it's repeatability over time, back to the points in the slides earlier. It empowers co-line multimodal sensing. So to Evan's point around how we do calibrations, how we do bore site calibrations, and how we bring that data together, it allows us to fly 3 very complex systems and align that data to a high degree of accuracy. So therefore, it enables multi-temporal analytics, which is critical to many environmental and agricultural or natural resources applications. And it saves a lot of time. Back to Evan's example from Cokery, in production agriculture or by using some lower grade tools, if your data is constantly off 3 or 4 meters in multiple directions, you spend a lot of time with brute force data management getting all of your data to line up. With this approach, that's not needed. So it saves you a tremendous amount of time. And that then reduces the gap between acquisition and analytics. So you can really jump on that analytics much more quickly because you don't have to worry about the data management side. And then one, which is something that most people don't think about, you know, in an environment like this, there's lots of data that's being collected. Some of it's being written in books, some of it's being collected with sensors, some of it's highly accurate, some of it is somewhat subjective. And by being able to provide these data sets, you have a source of truth. And that truth is where everything is in the real world, which means you can line everything up to that for advanced analysis. So, you know, this is a sample of some of the value propositions for direct georeferencing and what we're doing in agricultural research. Obviously, some of these are more important for others. But with that, I'll stop. I'll turn it back to the Applanix team, and then we can open up for Q&A.
Thank you very much, Matt. Okay, so questions. Let's just go to that. If you can see my screen here, we're at question time. Kurt, if I could turn to you, do you have any questions right now? And I certainly want to encourage any of you, if you do have questions about any of the material, please just enter that in the questions box, and we'll try to answer them, and we'll go from there. So Kurt, let me just see if
Yeah,
we have anything. Yeah.
yeah. There's nothing right now. Most of the questions that were coming up were related just to other stuff. So there's nothing yet for content. So if there is any questions based on what we've seen, happy to kind of address these.
Okay, well, maybe I can just start off with one that I was kind of curious about. Matt, what kind of gains do you think farmers or those in the agricultural industry are achieving now with using systems like yours? I.e., what kind of value is that bringing over what they had before? Is this really kind of helping them to produce more, save more money? What are the big factors there?
Yeah, sure. It really depends on your perspective. And so from a research perspective, obviously you're working towards advancing some of those breeding selections. So for example, plant height. Again, this is manual. So you're going out there and you're measuring with a stick, with a measuring tape, how tall is that plant? How wide is it? How many leaves? And so that limits your ability to go across thousands and thousands of experiments. So if you can automate that, you can then, one, do it over more ground, and then two, you can reapply or reallocate that labor to something else that's important. So that's just one example from a breeding perspective. From a monetary perspective, yield is always important in these kinds of applications, but profitability is really what matters. And so that comes from lots of different ways, but can we be more efficient with our water? Can we be more efficient with our nutrients? Can we detect disease earlier to then time applications for fungicide, for example, or determine that we don't need to apply that, which has immediate financial impacts. So those are some of the short, immediate kinds of things that we're seeing. The longer term, back to precision agriculture. Now, I mentioned that these are 4 to 6 years before the farmer gets that seed. If you can cut a year off of that breeding cycle, that helps the seed companies be more profitable. But it also gets seed that is right for the environment, right for that area to the farmer even faster. So that helps them be more productive. And then you have massive sustainability applications. So we're starting to not only do trials with things like what we showed today, but larger agricultural research trials on nitrogen, for example. So what types of delivery methods, what types of products are the most efficient? What is the balance between the amount that I need, the cost of that, and how that plant is uptaking that nutrient? And then can we then be better stewards of our resources as we're applying those kinds of things? So those are just some quick examples, but it also shows the diversity of the needs in this community, which is why we have focused on these tools that provide quality and ease of use, because everybody has slightly different needs and outcomes, and we're trying to provide them the best tools that they can to achieve those outcomes.
Absolutely. So certainly this is really applicable technology, especially in today's world where we're looking for so much more to come out of our agricultural industry, given the events and supply chain issues and weather, climate change and everything. So yeah, anything that can yield more and save more money is certainly beneficial. Anyways,
Yeah,
just
and
before,
I'll
sorry.
add one more point to that. You mentioned remote sensing earlier, and so this is not, in any way, shape, or form expected to sit stationary kind of on the spectrum of knowledge. So I think as you're seeing a lot of companies that are out there doing amazing things like drone deploy, and a lot of the agronomic companies that are working at the producer level, when we're working at the research level, those lines are going to converge. And so the lessons learned from hyperspectral, costs of equipment are going to continue to go down. And so over the coming decade, these technologies will blend more and more and more. And to your point earlier, satellite and other applications will continue to be a part of that.
Absolutely, absolutely. Well, it's a really exciting time. So, Kurt, yeah, any?
Yeah, we do have one question that came in. It seems like it was more directed for Matt and Evan. It's just asking, they're asking for a better explanation of your business model and just additional details on, do you sell hardware, or is it direct your or more of the service side of things that you guys are going to be?
Our primary intent is to sell hardware and software as turnkey solutions. Doing this academic or doing this type of research requires that you've got the right people and the right equipment at the right time, which means you really need to have that hardware in hand. So that is our primary focus. We sell, kind of standard integrations. We also do custom, as Evan mentioned. We've integrated several M600s, but we're also doing the Alta X from FreeFly because, again, of that being agnostic to platform. So that's really our focus. For drone as a service, that really started off as for us, working strategically with customers, helping to understand their needs, making sure that they knew that these tools would deliver. What we're finding is that more and more customers just don't have the internal capacity, or there's a bit of an apprehension towards capital expenditures, CapEx, and so they need that drone as a service model. So increasingly, we are doing both, but we'd be happy to talk with you if you're interested in an actual hardware solution.
Awesome. Okay, well, I think we're actually approaching the top of the hour now. So as planned, I think we'll wrap up. I just have a few more concluding comments here. Certainly, where can you learn more information from Griffin? www.griffin.io, and certainly from Applanix, applanix.com. We'd be happy to answer any questions you have. Certainly, from the Applanix side, if you're interested in learning more about direct georeferencing, we do have a webinar center where we talk about all of these technologies. We talk about the integrated GNSS, INS systems we have, the correction solutions, the POSPAC processing software. We have training videos, educational videos, and a variety of different webinars that just walks you through the technology. So that is a resource you can use. You can also contact Griffin directly, as Matt has suggested, or if you want to learn more about the actual core direct georeferencing technology, we'd be happy to speak with you as well. So we certainly thank you all for attending. This, as I say, is the first in a series of application-oriented webinars that Applanix is going to sponsor. So look for our next one, probably in the summertime we'll have that. And once again, thank you all for attending. We really appreciate your time and hope to see you soon.